So most of it, as you already know, what is organic chemistry? It's nothing but it's the study of or chemistry of carbon-based compounds, which mostly comprises of carbon and hydrogen. I told you it's a long form chain of carbon
Yeah,
and hydrogens. Okay.
it's just an
And
ongoing form of those.
yes. And one more thing that I mentioned in the beginning of the topic is most of the substances or materials around us contain carbon in it.
Yeah,
Okay.
so
And
everything is hydrocarbons, really,
yes, hydrocarbons.
except
So
for carbon dioxide, right?
yes. Not only carbon dioxide, there are so many other substances as well,
Oh,
which may not be hydrocarbons. But he says here over 90% of almost 92 million known compounds are organic. Okay, so that's a huge, huge number here. Okay, so then coming to the organic chemistry overview, we lost a slide here, did we? Yeah,
no.
okay, fine,
Oh.
yes. So as he says, organic chemistry, the study of carbon compounds and their derivatives, okay, from which they are derived. Okay. But basically, again, that is primarily hydrocarbons, as the name suggests. It consists of carbon and hydrogen, may also contain. Okay. Basically, you have carbon and hydrogen in it,
Yeah.
and the other elements that might get attached to it. It depends. Okay. Might contain nitrogen, oxygen, halogens, phosphorus, silicon, and sulfur. What are halogens?
Isn't that like,
Hmm. What are halogens?
are they the full? Oh no, that's noble gases.
Then,
I don't know what halogens are.
you know, where are they found actually?
Deep inside Earth,
A little bit close to it.
but in the ground.
They are mostly salts, okay, because they produce sodium salts of similar properties. Okay, so they're found in the yeah. So apart from the earth, I mean the ground. What are the other bodies that can be found?
Atmosphere,
No, it's connected to your earth.
plants.
No,
Then I've got no idea what else is connected to the Earth.
the sea waters.
Oh,
Yes, understood. So
so like
mostly it
oceans?
is got yes. Basically, it is got from there. Okay,
Oh,
so basically when halogens reacts with metals, they produce a wide range of salts.
mm-hmm.
Okay, the calcium fluoride, sodium chloride, silver bromide, potassium iodide. Okay, and you have a specific table in the periodic, I mean, the long form table as well. Okay,
Yep.
so yes, so this is basically halogens. So it's a chemical element that forms a salt when it actually reacts with a metal.
Okay.
Okay, yeah. Now, on to the next part in this. He says there are about 10 times more organic compounds known than all of the organic compounds put together. So it's approximately like 20 million compounds. So it's a very, very huge number.
Yep.
And as been said, carbon forms strong bonds with many other elements and with itself. We have seen carbon carbon single bond,
Yep.
then carbon double bonds, and carbon triple bonds. So single bonds between carbon atoms, they form alkanes. Double bonds, alkenes. If it's a triple bond, it forms alkynes.
Times.
Okay.
Yep.
And that's what he said in the next line. Carbon has a variety of bonding modes which allow great structural variation. That's the reason it's a very versatile element. Carbon. The most expensive substance that you get on this planet is nothing but a form of carbon, which is the hardest substance on this earth.
The hardest, but it's in everything.
No, it's not in everything.
Well, most things.
No,
90% of the things.
no,
Okay.
yeah. It's completely made up of carbon and it is the hardest material found on earth, found in Earth. I will not say on Earth, in Earth.
Volcanoes.
No.
Diamonds.
Yes. I was actually going to put it in a very different way, being more dramatic, but well, you gave me the answer. Fine.
No, I
Yes,
was going to go
diamond.
to volcanoes and I was like, maybe it's diamonds, but I'll give it worth
Yes,
of shot with
diamond.
volcanoes.
Because of its tetrahedral structure. Okay.
Because
It's nothing but it's
carbon.
yes, it's an allotropic form of carbon. You know what's allotropy, right?
No?
Occurrence of an element in various forms.
Oh, okay. Yep.
Yes. Now the pencil which you use to write contains graphite, lead and graphite.
Lead. It doesn't have
So,
any graphite anymore though.
so yeah. But there is a small amount of graphite also in it. So
Oh.
that's again carbon. Okay. So most of the substances around us, they do contain carbon. So that's the reason I said carbon is a very versatile element. Okay. So
So carbon itself
hydrocarbons,
is actually pretty hard. When
yes.
you're looking at like,
Yeah. But then again, I said it depends on the form it actually exists in. So
so it can
diamond,
exist in
it's
a
yes.
gas or a solid or a
Yes.
liquid.
Yes.
Oh.
Okay. So next what he says here is the unique nature of carbon or carbon bonding in organic carbon is. Now he says carbon forms bonds to itself. Yeah, we have seen alkane, carbon-carbon bond,
Yep.
single bond, alkene, double bonds between carbon atoms, alkynes, triple bonds. So it can bond with itself and form single, double, and triple bonds. It can bond with hydrogen to form hydrocarbons. Then you can have even carbon bonding with other elements. Again, you can call it as heteroatoms. That it can form bonds with metals as well.
Yeah.
Okay.
Wait,
So
does that mean like even after the three alkane kinds and whatever, there's
hydrocarbons.
aromatic and it continues going? Is that like 4 carbon bonding, 5 carbon bonding? Does it just continue going, or is that like
4 is the maximum.
oh, so then
Okay. Yeah. Yes, it can even form multiple distinct chains, of course. Okay. But one carbon atom can form a maximum number of 4 bonds. Okay. And suppose if you have multiple carbon atoms, then it can form a long chain. And that
so
is
then
what, yes.
even past the aromatic, then what are the definite? What's the point of those then? Because the first 4 is like single, double, triple bonds, and then what's the
And then
point of
4. That's 4. Because if you look at the configuration of carbon, 6
Yeah.
being its atomic number, and there are 4 electrons in the outermost shell.
Yes.
Okay, so it can at the most form only 4 bonds. That's it.
Then what's the point of the other ones? Like there's
So then,
alcohol there.
yeah, then what happens here is you have a hydrocarbon. To that, a functional group can get added, which changes the properties of carbon then.
Oh, so the rest of the functional groups just
Yes,
change the
yes.
properties.
It might be an aldehyde, it might be a formaldehyde, it can be an alcohol group. Okay, so they get attached to that, and then the properties keep changing.
Okay.
Okay. And again, it further says carbon atoms can bond together to form stable extended chains of atoms. When I say stable extended chains, for example, polymers, like you have this plastic bags.
Yeah.
They are a very fine example of stable extended chains. Then you have ring-like structures. Benzene, cyclohexane.
Is benzene connected with aromatic?
Yes.
Okay.
Then of course we have multiple bonds that carbon actually can form. Okay, that's another example. And then
The hybridization she was talking about, and I completely lost her. 100% I
is
lost.
it okay? Now I'm
Yeah,
going to explain that
I
to
was
you.
really
Okay?
bad at hybridization.
No, I'll explain that in a very nice
Like
in-depth
I know
way.
my SPs and then P blocks and etc. etc. But once it
Yes.
gets like confusing, I lost her.
No, I'll tell you. I'll explain it in a very detailed way where I think hybridization should not be a problem at all. So let's see this one first. Okay. What
Yeah.
exactly is this? And as you said, your teacher went too slow. Yes,
Yes.
he had a point here. Now, try to understand this first. So this is its atomic number.
Yep.
And this is its atomic mass.
Yep.
Okay. So atomic masses, number of protons and neutrons. Fine,
Yes.
understand that. Now, yesterday, as I said, 6 electrons. Or
So
6
2
is
and
a,
4.
yes, it can be 2 and 4. Again, in this 4, we have this 2s2 and 2p2. Now,
Yeah.
here is what you have to try. You should understand what exactly hybridization is. Okay. So I'll just move away from the slide here right now and then just go back to one screen here and try to explain
No,
what
because I
exactly
understand when you drew the blocks, because I understood that
is.
when they get connected,
Mhm.
that's how they have the share and the
Yes.
chain like gets
Yes.
corrected.
But there is something else when it comes to hybridization. What exactly is this? Now, S is not further divided. The
Yeah.
S orbital contains just 2
One.
electrons in it. But P is divided into further 3 suborbitals. Okay.
Okay.
Of course, 1s, we have 2 electrons in it. Here they are. And 2s contains 2 electrons. Here there are. Now, what
Okay.
about 2p? P also contains 2 electrons here. This is px, py, pz. And the rule here says when there are only 2 electrons, you just can't fill 2 electrons into the very first one. This is not possible.
Yeah, you have to put them
Yes,
separately.
because it has to come into the next one because there is something called degenerate orbitals. So what does this
Okay.
degenerate means? That means orbitals which have got the same energy. So here we are trying to distribute these electrons one by one into each of the suborbits.
Yeah.
Now we'll try to, now if you look at the entire second level, I find something not perfectly balanced here.
So isn't that like, can't you take
So
it out of like
yes,
2s2?
yes. So what can be possible here is now there can be a redistribution that can actually take place. Try to understand this. Now, what do we mean by redistribution? Can you see this electron over here? This electron will now just come out and then redistribute itself into this
But
orbit.
then
And
2s,
now,
it will be
and
2s1, right?
yes, but why did this happen? There's a lot of difference between, let's try to get this, clear this up. Yes. There's a lot of difference between this one and this distribution. Can you see here? I have something quite unbalanced here, right?
Yeah.
So I have an orbital which I cannot call degenerate. So the bonding also is too difficult here in this situation. So what happens in hybridization is there is going to be a redistribution of electrons. So this electron, which was over here, redistributed itself into the last orbit here.
Yeah.
Thereby, all these suborbitals now have got 1 electron each.
Except for 1s2, right?
We are not
What is that?
concerned with 1s2. Why? Why?
That
Because
one's always full.
right, yes, try to understand. If this is a nucleus, okay, this is your first orbit and this is your second orbit.
Yeah.
Whenever bonding takes place, we are only concerned with the valence shell. Valence shell is the outermost shell. We have got
Okay.
nothing to do with 1s at all.
Yep.
All that we are concerned is with the valence shell and the electrons that are present in the valence shell.
Yeah.
Understood? Suppose I'm not talking about carbon here, maybe some other element whose outermost shell is 3s. So obviously 1s is completely filled, 2s also will be completely filled. Then we should be concerned with
So always the valence
third
shell.
one. Yes, the outermost shell or the valence shell, as we can call it technically. Understood this now?
Yep.
So we are not concerned with what is going on in 1s2. Obviously 1s2 will be full. Okay, that's the reason the electrons now will get into the second shell or to the
Yep.
second energy level. Understood this point?
Yep.
Why the redistribution actually takes place? Redistribution should take place in order to get degenerate orbitals. When I say degenerate, it means orbitals having the same energy level. So each of these orbitals now have got one electron each. That means their energy levels are same now. Okay.
So what if there was like 5? What would you do with that?
Then
Or would
wherever
you
it
just
is
add one
possible
more
to
P block?
redistribute, yes. No, not one
Oh.
more P there. So how
Would-
far the redistribution can take place, then it redistributes itself to that extent. But when it comes to carbon, this is what? because you can't have 5. How can there be 5 electrons in the outermost shell in carbon? Because carbon at the most should have 6, isn't
Yeah.
it?
Yeah.
All in all, it can be 6 and 4 in the outermost shell. Now, if you say 5, then it should be nitrogen.
So then what would you do with nitrogen then?
No,
Because then
that's a different story again. Okay.
oh, okay.
Okay. Let's now concentrate on carbon. Okay. So here, how this sp2 sp3 hybridization takes place is like this. Okay. Is this clear?
Yes.
Fine. So let me go back to the slide now. That gives a very clear picture now. Come on. See this. So what he says, a carbon atom has 4 valence electrons. Therefore, it needs 4 more electrons to fill its valence energy level. So try to understand. If I just go back to the earlier page here, how many electrons should be there in each of these
One.
orbitals? No, how many should be there?
Well, 2.
2. So how many
Yeah.
are there at the moment?
1 each.
So it needs one more to get into a bond formation, right?
So then it
So it exactly will be on a
binds again.
lookout for another carbon atom in the same state. Understood?
Will it only prefer carbon atoms, or will it also want to take like
Mostly carbon atoms, because see, try to understand one more thing in chemistry. The bottom line in chemistry is atoms, they will try to enter into a bond formation with other elements, atoms of other elements, in order to get an octet configuration.
yes.
Now, when I say octet, it means in the outermost shell, it always tries to get a configuration of 8 electrons.
Yep.
Now, how many are there in this?
4.
So when it enters into a bond formation with a similar atom, so how many will it total up to?
8.
Got the point?
Yep.
Yes. Understood?
Yep.
So this is how it works out. Okay. Its target will be 8 always.
Okay.
Understood?
Yep.
So let's go back to the slide. Here we go. So carbon atom has 4 valence electrons. Therefore, it needs 4 more electrons to fill its valence energy level. So as we
Yes.
saw in this hybridization just now, where the redistribution took place, so in each of the orbitals, there were only one electron. So it needed 4 more to, complete that or reach that octet configuration. So try to look out here now. There's something interesting here. See, how many do we have here? So if you can see, can you understand anything with the dot and the cross?
Oh yeah, that's a Lewis dot structure.
Yes. No, but what does the dot indicate and what does the cross indicate?
Well, dots for one carbon and crosses for the other, so then you
For the
can
other,
see the
yes.
bonding.
Electrons taken from the other carbon atom. Okay. So by this, what happens is it completes that hybridization structure. So these are the possible ways the hybridization can actually be reached. Okay.
Wait, what about when you're doing like alkynes? They've got triple bonding. When you're bonding 3 carbons, wouldn't only 2 carbons be like full? You would still have that 1 carbon. Oh, that's why it goes up to 4. Okay.
Yes. So now moving on to the next one. So that's what it says. See here. The very first line clears it up. The process of mixing orbitals as atoms approach each other is called hybridization. So we have mixing orbitals here. We saw that from 2s, 1 electron redistributed itself, okay, in making all the orbitals degenerate. Okay.
Yeah.
So next what it says, mixing the s and p orbitals results in 2 new orbitals, which are hybrids of the 2 original ones. See here. Because what happens is, let me just tell you. Normally an s orbital is a spherical shaped orbital. Okay. And then when you talk about p orbitals, they are dumbbell shaped. Now, when you have an hybridization taking place between these two, the result of, these two combining itself, then they look something like this.
Is that how you would draw it?
Yes.
So if there's like more than just like one sp hybrid orbital, would you just continue like drawing more and more of those?
Yes.
But they'll attach to each other, right?
Yeah, yes, absolutely. So we just take one for the sake of, example for sake of understanding and how exactly it takes place. So that's what he says. Now, when they completely hybridize, there's a lot of difference between this one and this one, because this is a huge sp hybrid orbital. Okay, so you can
Yes.
see lobes are quite larger than the normal p orbital. Okay,
Yes.
and here also you can see one is rounded and one has a larger lobe. Okay, so I think you understood what hybridization is basically.
Yes.
Okay, now is this what I explained just now?
Yes.
It's the same thing, right?
Yes.
Yes, as you can see here. Should I tell you something?
Yes.
This is for class 10 back here in India.
We only learned this like very thoroughly, not even thoroughly, but last year in year
Yes.
11.
Oh, okay,
But do you guys
fine.
stop at class 10? And then do you
No,
go straight on to
no,
university?
no, 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 no.
Oh,
I'll tell you. No. First of all, I have to just pause the recording before I say this. Okay. So, so I think this is clear, right? You understood this
yes.
part. So, how the promotion of an electron from here redistributes, and then you have the what do you say? All the degenerate orbitals now. Okay.
Yep.
Of course, after that, what we have is the sp3 hybridization. It's the same thing again. Okay. This is, of course, in methane.
Yep.
Yeah. So you see there are three p orbitals. Because always try to understand s orbital contains 2 electrons and p orbital contains 6 electrons.
Oh,
So
in
why
total.
how 6? Because this p is further divided into 3 substationary states again. Px,
Okay.
Py, and Pz. That is what is this. This is Px, this is Py, this is that Pz.
Then why is it that they'll mix it and then add one more so then now it's P4?
So that's the reason it needs to be of equal energy. That is why I
Oh,
use the
so
word
it's forced to go into
degenerate.
another one.
Yes, or else it cannot enter into a bond formation. Okay, and upon this, now if you look at it, let's try to understand. Muskan, I think I think this answers it all actually. Now, can you tell me how many electrons it needs to complete this bond formation?
8 in total.
8 in total. So it has already got 4, right?
Yep.
Can you tell me what is the atomic number of hydrogen?
Isn't it 1?
Exactly.
Yeah.
So hydrogen has all got 1 electron in it. Okay. Now, do you just another question here? The nearest now always an electron, an atom, okay, tries to get the configuration or tries to get an atomic number of the nearest inert gas.
Yes.
Now, why I'm saying 888 here is because for carbon, the nearest inert gas is neon.
Oh,
Yes,
yeah, it is.
carbon, nitrogen, oxygen, fluorine, and then neon. Neon is 10. Okay, so that's the reason it tries to get that configuration of neon. Okay. And so
Yeah.
what happens here is, so now where will it get these 4 more electrons from? So see what happens in
Hydrogen.
methane. What happens in methane? There are 4 hydrogens which actually are getting attached to this now. So
Also,
it's not going to be a two-way process, because try to understand, hydrogen, it has got only 1 electron with it. Whereas how many should be there in a substationary state?
2
2. Where will it get another one from? Where
from.
the one which is already there in carbon. So here it's a mutual sharing between the two.
So that means hydrogens will be 1s2 while carbons will be sp.
Yes. I mean,
Hydrogen.
it reaches the configuration of neon.
Yes, but like
Yes.
carbon's on like sp while hydrogen's only starting at s block.
Yes, they're starting in this block. Yes.
So that doesn't matter that they're two like different levels.
Yes. Yes. So that's the reason we see the name what he has mentioned very clearly. sp3 hybridization. Okay. So in the
Oh, right. Yeah.
yeah, so in the process, what happened now? Hydrogen becomes helium. I mean, doesn't become helium. It gets the configuration of helium.
Oh, yeah.
It had only one electron. It shared one more from carbon.
And then
Carbon
now it's
also, and then vice versa. Carbon had one. It got one more from hydrogen. It got the configuration of neon. I mean, on the whole.
so even though it like gets so most of like the atoms want to have the configuration of like the noble gases,
Yes.
whatever's the
They,
closest to them. But
every
they won't
yeah.
turn to them, right? Like this won't turn into like helium or like
No, no, it doesn't turn
neon.
into it doesn't turn into helium or it doesn't turn into neon.
Okay,
Okay.
but that's like their inspiration.
Yeah, no, not even inspiration. What I said is it doesn't become neon or it doesn't become helium. It gets the configuration of helium
Okay.
or it gets the configuration of neon. So it doesn't mean that it becomes neon or it becomes, what do you say, helium or for other reason like argon or krypton or radon or xenon. No, they're not going to become like that. But yes, they will attain a configuration so that it becomes an octane and becomes a stable atom there. Understand? So to attain that stability, this is needed.
Okay.
Okay. So this is an example for methane. So methane, very clear. CH4. Why CH4? Because there are 4 carbon atoms which have got unpaired stationary states, substationary states. So that's the reason 4 hydrogens get attached to it, and that completes the configuration, and that becomes something new. So what is CH4? CH4 is methane, a stable hydrocarbon
That's an
again.
alkane.
Yes, it is an alkane.
But then it's a single bonding.
Yes, see, these are all single bonds here. It's a one electron entering into a bond formation. Okay.
So then when it's double bonding, is that just 2 carbons connecting to another? Okay.
Yes, yes. In
All
fact,
right.
yes, you have a double bond emerging between that. We'll come to that as well. The same thing over here now. Okay. This is again sp3 hybridization.
Why does it matter about the 109.5 degrees?
That's the angle at which the bond is actually forming.
Why does it really matter?
Yes, it does really. You have to know that what is the angle that it forms, because 109.5 is one. We again have more, like most of the elements, atoms, when they get into bond formations, it creates an angle depending on the type of hybridization actually. Okay. So here, if you look at it, here, if you see the first picture, it hybridizes to form 4 sp3 hybrid orbitals. Okay. So when all these 4 come together, it gives you a picture like this over here. And thereby the angle that is between these lobes, for example. Okay. So obviously, yes, there will be a, because it is now attaining a geometrical structure. Okay. And so obviously I mean, there will be an angle between these, orbitals forming. Like for instance, here it's 109.5, or else if you look at the next slide, okay, we have a bond angle of, because there is a double bond here. Try to understand. There is a double bond here. We only had
That's why
single,
it's
we had a
120.
single bond here. So see, the angle is now changing to 120 degrees. Okay.
Okay.
Now there's a change here. Here it was sp3 hybridization. Here is talking about sp2 hybridization. Okay. So that also does matter. Okay. We have gain. Let's see what happens in sp2 actually. See here. This is what happens. So redistribution takes place. We have these 4 electrons here now. Okay, one each in each of these shells, and then they combine with hydrogen. And try to understand. You said there are 3 sigma bonds forming. I told you yesterday what are sigma bonds and what are pi bonds. Okay.
Yep.
If it's like an end on end overlap, then this is
That's
called
like
as sigma. And if it is a side on overlap, then we're going to call it as a
and
pi
sigma
bond.
bonds are stronger.
Exactly. Pi bonds are weaker because the extent of overlap is also quite less. So in sp2 hybridization, the bond angle is 120 degrees between these two.
Okay.
Okay. And what's the next one after this? Yeah. Example, ethene, acetylene. So
why is it
carbon.
so significant in organic chem and acetic acid? I think it's
Acetic acid. Acetic acid is different. It's CH3COOH.
yeah, like I don't know. My teacher was like going on about like pharmacists and how like every pharmacist needs to know about the acetic acid because apparently that structure can be changed by them, therefore it gets
Yes,
changed.
yes, it is possible.
So why is that so significant in like organic chem, acetic acid?
I mean, especially in pharmacy.
Yeah, apparently because the structure can be changed by like just anyone.
Did she say that? The acetic acid
Yeah,
structure can be changed.
yeah.
How can they change it?
I don't know. But apparently every single pharmacist knows the exact structure of acetic acid. It's acetic acid or acetone, one of those.
I think it must be acetone.
But I don't know. But they can apparently like manually change it. I don't know
Must
how,
be
but
acetone. That must be acetone actually. But I don't think that they can manually like have it changed or something like that. Are they supposed to do that?
I don't know. I've never heard of it.
Okay. So this is sp hybridization. As you can see, a triple bond exists between two carbon atoms here.
Yep.
Then let's see this one.
Do you think I'll have to draw one of these?
No, if you can even understand. Now, why he says this is because try to understand something here. Okay. So here it says sp atomic orbitals overlap head on. Now, when they say head on,
Yep.
as you can see here, where is my annotation? Okay. This is one head on that takes place between two carbon atoms over here. So that's the reason we have one sigma bond here.
Yep.
Okay. This is also one head on here. Okay. Understood that?
Yep.
So this is how it takes place. So if you just go back to the previous page. Yes. The same thing has been explained here as well. Okay. So 2p and then 2 degenerate orbitals of s and p here. Like what it's trying to say here is when you talk about hydrogen, it is s orbital. Okay. It enters into a bond formation with a p orbital. Understood? So this is a sigma bond here. Then between two p's over here as well, there is one sigma bond. But then
Yep.
here, not in this case. Okay, here between these two, we have a pi bond formation.
Is that just an imaginary one?
Exactly.
Is
They
that
more or
just because
less
they're like exactly at the same
no,
probably degree or something?
yes, they more or less will look the same,
Yeah.
but he has made it colorful for us to understand. Okay, but they roughly have this, double-shaped image.
But they're not actually connected.
They are indeed connected. They do overlap. Okay,
Oh,
but that is at a very, very atomic level where you physically will not be able to see this happening. This is just what we have imagined. But yes, the overlaps do take place. The sigma bonds and pi bonds do form in them because it has been
okay.
studied now. Yes,
Oh well.
that does happen. So here, these are some of the combinations. Okay. So he says organic compounds can comprise a near limitless set of combinations and possibilities. Okay. It can just go on and on and on and on and on. Okay.
And then we're supposed to like draw like the hybridization for all of these.
Yes, we do have a set of rules, like for example, I think the next one, or I think it's slightly more further here. When you have this nomenclature, which will be actually coming across. Yeah, see this one. This is what the chemical structures. So he says shorthand diagrams. You also have to like learn it, how to draw them, okay, how to name them.
That's what I think she said. We need to know
Exactly.
exactly how to draw them. for the
Yes.
exam.
Mhm.
Oh my God.
Yeah, this is another one. So based on these, so when you say draw, you're not going to draw these structures, but more or less you'll be writing these structures, okay? Like the branching structures over here.
Yeah, I don't
You're
understand
making
that. Like, how would
these.
you know?
Yeah. That is what I'm saying. So first you need to know the functional groups, those three, or what alkanes, alkenes, and alkynes. Understood? So once you come, we were talking about this yesterday.
Yeah.
Yes, right. Yes. So see this.
So I'm guessing like onto like a random branch, you just draw one
See,
branch with one
this is
short line and you're like, all right,
yes,
it's an
yes,
alkyne,
yes.
alkene.
So you have to write those structural formulae for many of these. See this. There are many like this now.
And then you're supposed to just tell them apart by the branches?
Yes, you have to literally name them.
But they don't have any like they don't have like any
See.
like the letters of the
No,
tooth or anything.
obviously you will have to learn that as well. You also
Oh,
have to learn that as well. Yes, absolutely. There are
oh.
rules for it again, which you will be explained.
Do you think you could send me the rules because I'm guessing it's not on here?
Oh, it's not completely given though. Quite a huge stuff.
Oh God.
Yeah, this one. So, for example, you can see molecular formula of butene, C4H8. So, how can you write? This is the condensed structure, of course. And you have to draw its real structure, how it looks like.
Yeah, how am I supposed to know what to draw?
That is why I'm here.
Yes,
So
that is
see, you
true.
have this IUPAC, which I was talking about the
Yeah, she
other day.
finally introduced it today.
Yes, yes. So you have the IUPAC names and how to actually write. See, this is what exactly the number, the substituent, stem, and its ending. So these are some of the rules which you need to follow when you write. See these. Okay. Don't worry. Don't be frightened by all these. Okay, because it's a step-by-step process. Nothing is going to happen overnight. Okay, it's going to come slowly and steadily.
Okay.
Okay. So I think today this is more than enough what you've digested.
Yep.
So
Oh, also next Thursday,
yes. Hmm.
I am actually staying overnight at school, so I won't be doing tutoring, at least in the afternoon. So we could probably have it in the morning and then
Yeah. Fine.
for next Thursday because we've got a
And
sleepover at school.
okay, you're allowed to.
It's for